In the beginning, there was nothing. No space, no time. And then there was light. Less than a trillionth of a second after the Big Bang, the marble-sized universe was very unstable and underwent an enormous growth spurt.
During this period of incredibly rapid expansion, space itself was expanding faster than the speed of light.
In the same way that this hot glass ball inflates, so did the baby universe, expanding in all directions at once. And as it expanded, it cooled. A trillionth of a second after the Big Bang, the universe was small enough to fit inside the palm of your hand. A tiny fraction of a second later, it was the size of Mars. Another fraction of a second, and the baby universe had grown to 80 times the size of the Earth. A trillionth of a second after the Big Bang, and our newborn universe was still expanding, but it didn't contain matter. It was pure energy.
Very quickly, distinct things begin to appear in that blur. Within the first second, energy itself shatters into distinct forces, including electromagnetism and gravity. And energy does something else quite magical. It congeals to form matter. Quarks that'll create protons, and leptons that include electrons. And all of that happens in the first second. Now we move forward 380,000 years. That's twice as long as humans have been on this planet. And now simple atoms appear of hydrogen and helium.
The universe created both matter and its arch-rival antimatter. And when these two met, they obliterated each other. The infant universe was a war zone, a battle to the death between matter and antimatter. If they mutually annihilated each other, the universe would remain full of energy, with no galaxies, stars, planets, or life. Fortunately for us, there was an imbalance. For every 100 million antiparticles formed, there were 100,000,001 particles of matter.
But there was that one extra particle of matter left over in each volume. And that was enough to account for everything we see in the universe today.
This tiny imbalance led to all matter we see in the universe: galaxies, stars, planets, and ourselves.
We are a little bit of debris left over from the annihilation of matter and antimatter. We're the leftovers of that process. If the universe had not developed this slight asymmetry between matter and antimatter, the universe would have been completely boring. There would be no structure, there would be no galaxies, there would be no planets.
Gravity is more powerful where there's more stuff. So where you get slightly denser areas, gravity starts compacting clouds of hydrogen and helium atoms. So we can imagine the early universe breaking up into a billion clouds, and each cloud is compacted, gravity gets more powerful as density increases, the temperature begins to rise at the center of each cloud, and then at the center of each cloud the temperature crosses the threshold temperature of 10 million degrees, protons start to fuse, there's a huge release of energy, and bam! We have our first stars. From about 200 million years after the Big Bang, stars begin to appear all through the universe, billions of them. And the universe is now significantly more interesting and more complex. Stars will create the Goldilocks conditions for crossing two new thresholds. When very large stars die, they create temperatures so high that protons begin to fuse in all sorts of exotic combinations to form all the elements of the periodic table. If, like me, you're wearing a gold ring, it was forged in a supernova explosion. So now the universe is chemically more complex. And in a chemically more complex universe, it's possible to make more things. And what starts happening is that around young suns, young stars, all these elements combine, they swirl around, the energy of the star stirs them around, they form particles, they form snowflakes, they form little dust motes, they form rocks, they form asteroids, and eventually they form planets and moons. And that is how our solar system was formed 4.5 billion years ago. Rocky planets like our Earth are significantly more complex than stars because they contain a much greater diversity of materials. So we've crossed a fourth threshold of complexity. Now, the going gets tougher. The next stage introduces entities that are significantly more fragile, significantly more vulnerable, but they're also much more creative and much more capable of generating further complexity. I'm talking, of course, about living organisms.
This young world is just moments away from its final act of formation. The burning sphere swells until it has eaten the sky. At last, with a deafening rumble, the two survivors crush into one another. Towering waves of material erupt and cascade into roiling chaos. Chunks of planet splash into orbit as the Earth devours its last meal.
Was dominated by volcanoes, hostile and lifeless. But deep in the oceans, life had begun. The latest theory is that chemicals spewing from underwater volcanic vents solidified and created the conditions needed for the first cells to form. For some 3 billion years, simple microscopic organisms were the most advanced form of life on the planet. Cyanobacteria and other oxygen-producing microbes began to bloom. These flourished in colonies of plant-like microbes that pumped out enormous volumes of oxygen. And it was this increase in oxygen that was the key to the rise of the animal kingdom.
Organisms started using oxygen to respire, yielding a lot more energy, which allowed the development of more complex life.
Just before complex life appeared, the world was in the grip of the biggest ice age in its entire history. And then suddenly, advanced organisms appeared.